So I would like to talk to you about a new concept called bitwise operators, interacting with the individual bits of a number. And then hopefully if there's time we'll talk about the next thing too. That might be next time though. So let us start. So bitwise operators, this is a new thing in C++ that you haven't learned yet. One of the last pieces of syntax you don't know. And the hint is in the word. We're going to be talking about the individual bits of a number. Do you remember what bits are? They're like, if you have a binary number, well, all numbers in a computer are stored in binary. And like here is our, here's an example binary number. And an individual bit of a binary number is a digit. Bit is short for binary digit. Okay. So let's review all that. Let's go back to all that because we need to understand binary again if we want to use bitwise operators. So yeah, a bitwise operator, it's going to be a thing that operates on the individual bits of a number. So a bit is a 0 or a 1 in a binary number. And so, for example, remember how to translate from a binary number to a decimal number? You start like 2 to the zeros place, 1 times 2 to the zeros, so the 2 to the ones place, 2 squared, 2 cubed, 2 to the fourths place, have another one. And so that's apparently the number 19. And then if we were doing this one, 1, 0, 1, 1, base 2, remember how to extract those pieces. This is 1 times 2 to the 0, plus another 1 times 2 to the 1 now, that's the 2 to the 1's place, plus 0 times 2 squared, didn't even need to write it, and then plus 1 times 2 cubed, that's that guy. Okay, and so that's going to be what? 248 plus 2 plus 1, which is 11. So that is the decimal number 11. All right? Remember, this is coming back to us. So, yeah, we represent numbers in a computer in binary, of course. Like every int is binary. And the number 0 is just a bunch of zeros as far as binary is concerned. We take up a lot of space, like 32 bits of zeros is your number 0. All right? We've also been only talking about positive numbers, so I might have to fix that in just a second. I've only shown you how to all right, this is how you generate a positive number. This is positive 11. How do negative numbers work? Because they're stored in binary too. We'll figure that out. And so just int by itself, right? If we make something that's an int type, that makes a box that holds positive, 0, and negative numbers. How in the world does it do it? So that's our next question. There are 32 bits to an int. So that means the number 0 in int land is 32 zeros. 32 bits worth of 0. So that's how you store 0 as an int. It's 32 zeros in a row. 32 zeros in the int 0. Because ints take up 32 bits. So even the number 0. 32 bits of 0. Alright, so how in the world does int encode negative numbers? Because it's just a bunch of 1s and 0s at the end of the day. How do we do it? So we can actually figure this out. This is exciting. We'll discover what negative 1 should be together. Alright? What in the world should negative 1 be? But it's 32 bits, right? Negative 1 is 32 bits long. Whatever it is, it's the number such that when we add 1 to it, it gives us 0, right? That's what it means to be negative 1. So let's discover that. Let's pretend, just to make it easier for me to draw, let's pretend we're working with 4-bit numbers. That's as big as our numbers are. They get 4 bits wide, and that's as much as you get. So let's figure out the number that we should have when we add it to question mark, question mark, question mark, question mark. When we add that to the number in binary 1, right? This is 0, 0, 0, 1, binary 1. We end up with all zeros. Because that would become negative 1, right? Let's just discover what it is then. This must be what negative 1 is. Whatever adds to 1 and becomes 0. Pretending we have 4 bits rather than 32, because that is simpler. So, alright. What should this bit be? When I add it to 1, I must produce a 0. Well, can't be a 0 then, because 0 plus 1 would put a 1 there. Alright, so this is forced to be a 1. The rightmost bit of negative 1 in binary is 1. Because that would force a 0 here. Does that make sense? Because 1 plus 1 is 2 in binary, and you'd carry the 1. Yeah, it's 1, 0. 1, 0. Cool. Now we have this one. What bit should this be? This is, again, we're trying to build negative 1. I'm trying to add 1 and 0 and this question mark and end up with 0 again. So again, this bit can't be 0. Does that make sense? Because that would force a 1 here. I need it to be 0. Negative 1 is the number which, when added to 1, produces 0. So I must have another 1 here. Do we see that? Because 1 plus 1 is 2, which is 1, 0, carry the 1. Cool. And again, playing the same game, I think you get the idea. I can't put a 0 here. I have to put a 1 here to force a 0 down in this position, and the 1 will get carried. Okay? Same for this last bit. We have 4 bits, let's pretend, in our numbers. So again, this can't be a 0 because that would force a 1 here. It must be a 1. And that would force a carry again, a carry out of a 1, but we only have 4 bits for our numbers. So that 1 just vanishes. Fine. And so this number is negative 1. Does that make sense? 1, 1, 1, 1 in 4-bit int land is negative 1. Any questions about that? So 111 also is the number 15 in binary. Does that make sense? So it's negative 1 and 15 at the same time, depending on how you think about it. We have given up some large positive numbers to store negative numbers. That's what we've just done. Okay? So yeah, negative 1 in binary, that's all 1s. Cool. And the reason it works is because of that last carry. It doesn't produce a giant number. We just don't have room for that last one. Cool. The final carry does nothing because we can't, we have 4 bits only, can't have a 5th bit. We only have 32 bits, can't have a 33rd bit. Okay, question?
So how does the computer tell the difference between 15 and negative?
It doesn't. C++ knows that you used an int versus an unsigned int, if you've read about that. And when it's printed, it knows the difference. But stored, it's the exact same binary encoding. It's just, when you want it printed, did you tell C++ that you want it printed as an int? Or as an unsigned int, which is only positive. Yeah, that's interesting. Let's discover what negative 2 should be. That's the number which, when added to 2 in binary, 0, 0, 1, 0, produces 0 again, right? So let's discover what negative 2 should be. So I need a 0 in this position. I finally can't put a 1 here. This can't be a 1 because that would put a 1 there. So this has to be a 0. And then, what should this one be? A 1 or a 0? Can you guys that are talking, please talk on Discord instead? I can't concentrate. Thank you. Alright. So this guy, I have no clue what it should be, but it's got to produce a 0 here. So it can't be a 0. 1. So it's the same game again. 1, 0. It carries. What should this one be? 1 plus question mark plus 0 needs to produce a 0 here. It's got to be a 1 again. See that? And we're off to the same race that we were at, and last time we have that last carry. So negative 2 in binary, in 4 bits of binary, must be this. Must be 1, 1, 1, 0. 1, 1, 1, 0 is equal to negative 2. It's equivalent to negative 2. It's also the number in big binary land. It's also the number 14, right? So we've given up the number 14 to store negative 2. And so that's the encoding that we've chosen. It's called 2's complement, by the way. The way that we're storing these negative numbers is called 2's complement. And there's actually a trick to compute it very quickly. You don't have to play this game all day long. Your computer definitely doesn't. So if you want to negate a number, turn it into its negative equivalent, you flip all its bits and then add 1 to it. All right. So for example, let's say that we started with positive 1 and we wanted to generate negative 1. How do I want to do this? So here is positive 1. I'm going to flip all the bits. That makes 1, 1, 1, 0. I flipped all the zeros to 1s. And then if you add 1, that generates 1, 1, 1, 1. So that was a very quick way to make negative 1. That's how you're doing it. That's the quicker way to do it. And then same for it works the other direction too. Doing it to positive 1 turns it to negative 1 and vice versa. We had negative 1, assuming we had 4-bit numbers. Flip all the bits to make all zeros. And then add 1. It's like, okay, yeah, that was negative 1 because now this is positive 1. Okay? So that's the quick way to do it. Are there any questions about that? So that's how negative numbers are stored. Negative 1 in binary as an int is 32 1s. It's 32 bits long. It's 32 1s rather than 4 1s. But I think you get the idea. Yeah? So that's kind of cool. Now we're ready for bitwise operators. So let's talk about the first one, bitwise AND. So AND is very similar to the logical AND that you know. It's all going to go back to the logical operations that you know. So double AND is a logical AND. Bitwise AND is going to do logical AND on the individual bits of 2 numbers. And yeah, so here's the idea. Sometimes it is nice to store things other than numbers inside of ANDs. So for example, instead of making 32 bool variables, you can use one int. Does that make sense? It can pack all that information together because you have 32 ones and zeros inside of an int. It could be on or off each bit. So you can save a ton of space because of that. So for example, maybe like here is your large number using an int to store a bunch of stuff about a video game that you made. You're trying to keep the memory down. So like maybe this bit means like that your character has an extra life. You can let each individual bit do something. So you have an extra life if this bit is set to 1. Or like your character is riding a horse if this is set to 1. 0 if it's not. Something like that. So you can use an int, like 32 bits, to store 32 Boolean values. And so then the question is, how do I extract? How do I know if that particular bit was a 1 or a 0? That's where the bitwise operators come in. So yeah, there are ways to do things with the individual bits of a number. Like I want to get the 12th bit. I want to set the 3rd bit to a 1. I want to unset the 3rd bit. I want to make it a 0. And bitwise AND lets us do a piece of that. Bitwise AND lets us do Boolean AND, which you remember, the truth table I hope for AND, on each bit of a number all at the same time. So 1 stands for true, and 0 stands for false. And bitwise AND is not the double ampersand, it's the single ampersand. So I'm so sorry. Yeah, this is the 3rd place where we're using this in C++, but you get it from context usually. So here's what bitwise AND does. So in addition to address of and reference, it does bitwise AND, this ampersand. And here's what you do. You give it 2 numbers. Let's pretend that I've written them in binary. If I bitwise AND this number with this number, pretending I only have 4 bits again, because it's easier for me. Let's say I have these 2 numbers, this number and this number. You can bitwise AND them together, and what it does is it lines up their bits, just like this, and it starts doing logical AND on each of them. So it takes these 2, it lines them up, the 1 and the 0. 1 is true, 0 is false, and so it does logical AND on them. It does true ANDed with false, and we all know that that produces false, right? And so what it does is it computes a 0 in this bit. Bitwise AND computes a new number, all right, given 2 original numbers. And then it's going to do this. It's going to line up these 2 bits. It's like, all right, that's a true. I'm going to AND it with true. 1. 1 for true. 0 ANDed with 1. False ANDed with true. False. And then again, true ANDed with false. False. So that produces this 3rd number. So apparently, what is this? 8, 9, 10, 11 ANDed with 6 produces 2. It's not mathematical at all. It's bitwise. All right? So that's the goal. That's what we just did. So in C++, if you were to do this, you'd say it more like this. I'd give 11 ampersand it with 6, bitwise AND with 6, and that produces 2. That's all base 10. It's a little weird, but you think about it in binary, okay? That's the goal. So bitwise AND is good for extracting the bits of a number to see if one was set or not. Here's the trick. Let's say I have this number, 1011 again, and I really want to know if this bit right here is set. You can't just look at it, right? I'm drawing it and we can see it, but inside of a variable, you can't just look at an individual bit. Say I want this one. There's a way to do it with bitwise AND, right? Here's the trick. First of all, here's the numbering. This is the 0th bit. This is the 1st bit. This is the 2nd bit. This is the 3rd bit. So I want bit number 3. I want to extract bit number 3 right now. And the way you do it is you bitwise AND that number that you want to extract the 3rd bit of with the number with a 1 in that position and that position only. 1 here and 0 everywhere else. Because watch what's going to happen. The 0 is going to kick out all the other bits. And so if this was set, it'll produce a 1 here. If it was a 0, it'll produce all zeros, which is the number 0. And that's what you can check for, right? So that'll force a 1 here. And so this is the number with the 3rd bit set only, because that's the bit I care about. 3rd bit set only. And so it will produce that 2nd thing if the bit was set. So you just check, was the result 0 or not? If it was 0, that means the bit was not set. Does that make sense? 0 is all zeros. And if this were a 0, this 1 would have done nothing. But because there's a 1, it'll pick it out if it's there. That's the goal. And so this is essentially what did we do? 11 bitwise ANDed with 8, and that produced 8. But it was non-zero. That's all we really want to check for. Okay? That's the goal. So that's what's going on there. Bitwise AND is good for bit extraction. Any questions about that before I show some code? all that same stuff. So yeah, the ampersand, so much stuff involved with that ampersand. So, let's see here. What did we just do? 11 ANDed with 6, that produced 2. 11 ANDed with 6, single ampersand. That was 2, and then this one was 11 ANDed with 8, and that produced 8. That's the goal. So I got my 2 and I got my 8. That's the syntax. Now you know. So because the result for that second one wasn't 0, well, because the result wasn't 0, bit 3 was set. That's how we know. And that's what you'd put in an if statement. Like, if bit 3 was set, this would be non-zero. Because 8 is the number with just bit 3 set. That's the goal there. Alright, so that's bitwise and. Of course there's bitwise or. That's exactly what you would expect. Instead of this double pipe characters, we chop one off. We make it a single pipe character. Bitwise OR operator is that. And it's going to OR together every bit. So like if we had this number 1001 and we bitwise OR'd it with 1100, what's going to happen again? It's going to line up those bits, takes 2 numbers and produces a third number. It's going to line them up, and it's going to do logical OR on each bit. So 1 is true, it's going to OR it with false, but at least there was 1 false. If there is, the whole result is true. So that produces true, which is a 1. Put the 1 there. And then here is 0 OR'd with 0. That's the only way to make 0, false. This will be 1, this will be 1, because false OR'd with true and true OR'd with true. There's a true somewhere, so it'll work out. So that is the bitwise OR. I hope that makes enough sense. And so what did I just do? This was 8, 9. 9 OR'd with 12. 9 OR'd with 12. Base 10. And that produced 13. So again, it's not mathematical at all. It's bitwise. Different. Any questions about that? So that's going to do logical OR on all those bits and produce a new number. So bitwise OR is kind of the opposite of AND. AND was good for extracting bits, seeing what was there. OR is good for setting bits, making sure there's a 1 somewhere. All right, so here's how you do it. Let's say I have this number, 1010, and I have bits 0, 1, 2, and 3, right? Let's say I would like to have this number, but I'd like to make sure that bit 0 is set. I want to produce the number where bit 0 is set of this original number, making sure that it's been set in there. What you do is you OR this with a number where there's a 1 in the bit you want set and a 0 everywhere else. Because do you see how the zeros will just let everything else fall through? Like if it's a 1, it'll make it a 1. If it's a 0, it'll make it a 0. And then for that 1 bit that you wanted set, it'll force there to be a 1 there because you are ORing with a true, guaranteed. All right, so that's how you set a bit. 0th bit. That's the number where the 0th bit is set only. Does that make sense? So essentially what we just did was 10 OR'd with 1. Oops. 10 OR'd with 1 produced 11. So that did addition this time, but not usually. All right. So yeah, that's how that works. That's how you set a bit. So let's show that. Oops. Boop. So this is, what did we do? We did 9 OR'd with 12, and we did 10 OR'd with 1. That's a single pipe character. So 13 and 11, just what we expected. And this one, force there to be a 1 in that position. Makes sure that the 0th bit is set. Alright, so that's that one. We good with OR? It's not horrible, I think. There are worse things, harder things to learn. There's one more that I care about teaching right now. It's called bitwise not. Bitwise negation, also called complement. Because the ampersand was logical not, and this is not duplicated, we we chop this off and we pick a different character, actually. So bitwise not, it takes one number and it's going to flip all of its bits. It's going to negate each of them. And the bitwise not operator is the tilde. It's the tilde character. So if you say tilde and you give it some binary number, or some number, it'll interpret it as binary, of course, and it'll flip all the bits because the negation of true is false and the negation of false is true. So this will produce 0, 1, 1, 0. There you go. And so apparently, what did I just do? This was 9. Negation of 9 was 4, 5, 6. So again, it makes no sense when you think about it in terms of numbers. Think about it in terms of bits. All right? And so let's do some bitwise negation. And then I also want to make a makefile just to have us practice that, even though it's just a single file. So see out the tilde 9. But this is interpreted as an int, so I will not get 6, because this was not 4 bits, first of all. It's going to give me something negative, all right? Because it's going to force a 1 at the first bit position. We've chosen that to be negative stuff. So this will make sense in a second. But tilde 9 produces negative 10. There's a reason. If you go back to the negative slide, there's a reason it looks like that. But we'll get there in a second, all right? So first thing I want to do is make a makefile. So let's do that. An example. Let's make a before we do, the 9. Tilde 9. What was 9 as an int, right? It was 1001, but it's 32 bits long. So there's a bunch of zeros over here to fill in up to 32 bits. And that's what we're doing. And we're doing tilde that. So what we just did is we produced a giant number, which we interpret as negative. Okay? That's what we did. All right, now for the makefile. So I'm going to make a file called makefile, and what you do is you make a target for what you want. You give a name. I want to make a file called bitwise, and then what does it require? Well, you could go through .o files, but since we just have one file to compile, you can start with the CPP file, bitwise.cpp, and then just how do we create it? G++, bitwise.cpp, -o bitwise, and now when I want to compile, it's very quick. I can say either make bitwise, or I can say make, because that's the first rule. It'll choose that. It's the first and only rule. So that's really, really nice. Really cute. That's my make file. Remembering all that. Can't forget. So, okay, back to this. Let's make a negate using to's complement function. Because what is negation, right? Negation is to negate a number, to multiply it by -1, one way to do it is flip all of its bits and then add 1. That's how the computer stores the negative version of that number. So that's why tilde 9 becomes -10, because it's 1 away from -9. We forgot to add the 1. That's how that works. So let's make a negate to's complement function. See out negate to's complement 9. This is what your computer's doing when you negate a number. It's really flipping all the bits and adding 1. So let's spell that out. Let's do it the hard way. So given some number n, let's give back the negative version. So I could just say return -n, but secretly I can do it using to's complement, because I know how it's being stored. Good bitwise example. So alright, how do I negate a number using to's complement? I flip all the bits, return tilde n, that flips all the bits, and then add 1, because it was 1 away from that negative number. And so this is just a very complicated way to print -9. So let me show that to you. Can I get both of those on the screen at once? Barely. Alright, so make to compile, and then I can run it, and I get my -9. So that's how you can, that's another way to negate stuff. Flip all the bits and add 1. Any questions about that?
Is there any scenario in which this would be better than just -9 or just returning -9?
No, it's the same exact thing. This is just spelling out what's happening. Yeah. Honestly, the compiler will probably translate this into a machine code instruction that does it all at once. But no, this is how it's stored, at least. And that's how we as humans think about it. That's all I'm trying to say there. Yeah. So, with all that, I have a question for you. I've given you all these things. You know, bitwise and, bitwise or, bitwise not. You've got all this stuff. I'd like you to come up with some code. You don't have to post it anywhere, but just like with each other, write on a piece of paper if you want. But I'd like you to write some code now that does the following. I would like you to write some code that unsets the 5th bit of an int named x. So I have an int x. I set to who knows what, could be anything, get it from the user maybe. How do you can do it in one line, by the way. You can be like x equals blank, semicolon. How can you make sure that the 5th bit of that int x is unset? So for example, if this were the number x, if it was this in binary, 0, 1, 0, 1, 1, this is bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, there's that one. That's the one I care about unsetting if it's set. I want to produce the number with a 0 right there and everything else the same. Okay? That's what I want. And I have a hint. Hint 1, you can do it with a not and an and. So you don't need bitwise or, but you need bitwise not and bitwise and. That's one way to do it. And then my hint for you, that's probably more useful, is you want to essentially extract every bit of this number except for bit number 5. Remember that and does extraction? So think about it that way. And so figure out a nice number to and with maybe. And not will help you create it. So think about that for a few minutes. And then I'll show you the answer. If you're stumped. But help each other. That bitwise and is the ampersand and bitwise not is the tilde. It's going to line up numbers, at least ands, line up numbers to logical and bitwise not. All right. Here's the idea. Did we come up with this? So let's say this is an example number, by the way. The number could be anything that we want to unset the 5th bit of. But if it's this one, here's what we would do. It should work. Your implementation should work the same for any number. Even if this bit is unset already, just keep it unset. 0, 1, 0, 1, 1. So again, this is bit 0, bit 1, bit 2, bit 3, bit 4, bit 5. There's lucky bit 5 that we'd like to unset. And one way to do it is to AND with, right, a number that takes every bit out but that one. So how would you extract every bit but this one? I'd make sure there's a 0 here to force a 0 when I AND. Does that make sense? And then how do I make sure that everybody else is as they were? I put a 1. Does that make sense to us? So I want a 1 everywhere except for this bit I don't care about. Because this 1, like if it was a 1 up here, it would be true ANDed with true, and then I get the 1 again. It would keep all the 1s, And all the zeros that were originally zeros, like the 1 wouldn't have done anything. It's still ANDed with false somewhere. And so I get my zeros back. So that forced a 0 in this position. And so here is your special number. Remember that if you have an int, you want a bunch of 1s this way too, right? It's 32 bits. It's 1s everywhere but bit 5. Does that make sense? That's important to think about. So what is this number? This is really a very long number. It is really a 1. It's a 1 right, or it's a 0 right here and a 1 everywhere else, 32 bits wide. The easy way to get at that is to start with a number with just a 1 here and a 0 everywhere else. That's easier to type, and then negate it. Does that make sense? So if I started with this number, if I started with a bunch of zeros and then a 1 right here, 1, 2, 3, 4, 5. So bit 0, 1, 2, 3, 4, 5. If I start with this number with bit 5 set and I negate it, do you see how that's going to put a 1 everywhere but right there? That's the easier number to come up with. Just negate that. What is that number with bit 5 set only and everything else is 0? That's 2 to the 1, 2, 4, 8, 16, 32. It's negation of 32. Or complement of 32. That one. So that's the number that you would AND with. That makes sense. It's easier, much easier to come up with than whatever it was. So what is, I don't even know if it's going to tell me very easily. It's whatever the equivalent of negative 33 is, and that's just a big long number. So that's not worth it. So x, I could, yeah. Honestly, it'd be easier to think about it as negative 33, even. But yeah, it would tell me whatever giant number it is, but we don't care. Easier to type, easier to figure out this way. I want to take my x and I want to AND it with the negation of 32. So that's the secret. Are there any questions about that now that you've seen the answer? It's a harder question for sure. Alright, if we are happy, what do we want to do next? So there's actually one more secret one that I want to tell you about now. It's called exclusive OR, XOR for short. So it's a different kind of OR. We have one kind of OR already. This is a different one. So let me show you the difference. Exclusive OR, and that's going to do bitwise exclusive OR. So here's regular OR. Remember the truth table for regular OR? If you have a number and or true and a false, and then you OR them together, X ORed with Y, what happens? What are all the cases? We have, if they are true, 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 false, false, true, false, false. What's the normal OR going to do? It's like if there's a true anywhere, it makes the whole thing true, and if they're both false, that's the one way to make them both false. Exclusive OR, that's regular OR. Exclusive OR works like this. Exclusive OR. It's a different kind of OR. Useful sometimes. If you had x, y, here's what x ORed with y would be. Boop. So true, 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 false, false, true, false, false. Exclusive OR works the same here, here, and here. It differs right here. Exclusive OR is like, it is true if one of them is true exclusively. If they are both true, I don't like that, and it becomes false there. That's the one difference, all right? So just that row. Are they both, if they're both true, does it make it true or not? Exclusive OR says no. Regular OR is like inclusive OR. They're both true. You can be true still. But exclusive OR wants just one to be true. Wants it to be true exclusively, all right? So that's one. That's that one. So regular OR is also called inclusive OR for that reason. And so, yeah, exclusive OR is true only if one of the sides is true. And there's no equivalent of like bitwise or logical exclusive OR. There's like that one for and, that one for or, that one for not. I guess exclusive OR with bools is essentially the not equals to operator. That's what exclusive OR is. And so here's what it looks like in bitwise land. The bitwise OR XOR operator is this one. It's the caret character. And now you know why you got a really weird answer if you ever thought that was the power operator when you first started out. It's doing bitwise exclusive OR, which is disgusting. That's very confusing to first-time C++ learners, I'm sure. So here's what it looks like. Like, I'm going to exclusive OR this guy with this guy. 0, 1. It is going to be, all right, true exclusive OR with true. Oh, no, they're both true. I don't like that, so false. Can't be true exclusively. Or can't be true inclusively. Only exclusively. So this one, they're different. Cool, 1. This one, they're different. Awesome, 1. This one, they're different. Also another 1. All right? So that's the idea. That's what we just did. Apparently this was, what? 8, 9, 10, 11. I just did 11 exclusive ORed with 5. And that produced 8, 9, 10, 11, 12, 13, 14. 14. Again, makes no real sense. So let's print that out. Exclusive OR is useful, I promise. It looks a little weird. But let me show you an example first. That was 11 exclusive OR with 5. Make. And I get my 14. Cool. One thing that exclusive OR is good for is that it's essentially doing addition. Exclusive OR is very close to addition in a real interesting sense. So, like, it's doing 1-bit addition is what exclusive OR is doing. It's like, all right, what's 0 plus 0? 0, right? Exclusive OR agrees. What's 0 plus 1? 1, right? Exclusive OR agrees. 1 plus 0 with a single bit. That's a 1. Exclusive OR is like, yeah, sure. 1 plus 1 with a single bit, you carry the 1 and the result is 0. Exclusive OR likes that idea too. See that? So exclusive OR is pretty much addition, and actually inside of our computers, there's a bunch of circuitry that's doing the addition. When we like tell C++ to add stuff, there's circuitry inside of our computer doing a bunch of exclusive ORs at once, and like moving the carried things as well. That's all addition is with a bunch of bits. It's secretly doing bitwise exclusive OR inside of our computers. That's how it's encoded. That's how it's performed by the CPU. So, if you like that idea, you'll have to wait until CSCI 45 to learn more. But cool thought. All right. There are some others. Honestly, this is a bitwise operation, but it's so useful. I don't even think of it as one, usually. Let's talk about shifting. That's going to give us the last powerful thing that we need to do bitwise stuff well. So there are two operators, the bitwise shift operators. It's the less than, and the greater than. And this is where they came from, by the way. So like your cout operator, your cin operator, give it information, extract information. They were originally in the C language bitwise operators that shifted numbers around. C++ was like, yeah, we'll use that for something else because you can overload them. That's kind of useful. But here, this is left shift and this is right shift. What left shift does is like shifts all the bits to the left. It really makes a lot of sense. So here's like, if I had this number 1011 in binary and I left shifted it by 2, what it's going to do is it's going to shift this number to the left, and that brings in some new bit positions, right? And it will fill those with zeros. So this will produce the number 1011, and then it'll put 2 zeros here. Does that make sense? That's what it's going to do. It's going to bring in 2 zeros because it moved those guys to the left. That's what happened. So this was the number 11, 8, 9, 10, 11, and I left shifted by 2. It produced this number, which is, let's figure that out. This is 1's place, 2's place, 4's place, 8's place, 16's place, 32's place. 32 plus 8 plus 4, that's 44. That produced 44. Do we see a pattern? What do we just do to 11 to make 44? We multiplied it secretly by 4. And what is 4? 4 is a special number too. 4 is a power of 2. Ooh, binary, I get it. Making sense, I hope. So left shift, what it does is it puts 0, and it's essentially multiplying by some power of 2. All right, so if I left shift, if I take a number, and I left shift it by some amount, some number of bits, that produces that original number times 2 to the I. So I left shifted by 2, so I multiplied by 2 squared. If I left shift by 1, that multiplies by 2. Kind of cool. Like if I took this number, 0, 0, 1, 1, and I left shifted that by 1, it'll bring in a new bit, 0, 0, 1, 1, new bit 0. Cool. And that is guaranteed to be This was the original number 3 times 2 to the 1. That was 6. This must be 6. Okay? Any questions about that? That's kind of cool. Actually, old CPUs or old compilers would, every time you multiply a number by 2 in your code, it would translate it into a bitwise shift inside the CPU because that was faster to perform than a multiplication. That's kind of cool to think about. So, yeah. The compiler knows best, usually. That's bitwise left shift. Let me show that to you. And right shift is exactly what you would expect. Yeah, it's going to be the opposite. So, see out. Here's 11 left shifted by 2, so that's multiplying it by 4. Cool, I get my 44. So that's that one, left shift. Here's right shift. Right shift is like this. Right shift is a little bit different. It is going to move, it's going to shift away things. It's going to bring in stuff on the left rather than the right and chop off things from the left. And so it's either going to bring in a 0 or a 1, depending on whether the number was negative. All right, there's a weird thing going on here. So let's say that this was my number. I had the number, I don't know, 5. Let's say I wanted 5. I had 1, 0, 1, and I wanted to left shift that by 1. So really this number 5 in int land looks like this. It's a bunch of zeros over here on the left, dot, 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 a bunch of zeros. What left shift will do is it's going to chop off this bit because it's going to bring in a new one on the left. Okay? And it will bring in a 0 because it was a positive number. All right? If it's a positive number, that new bit becomes a 0. Otherwise, it becomes a 1 to keep it negative. 0, 0. So this would produce the number 1, 0, which is exactly dividing by 2. So this was 5 divided by 2 to the power of 1. All right? So right shift divides by a power of 2. I hope that makes enough sense. That's going to give us our 2 back. So int does that. If you right shift on unsigned ints, and unsigned int can't be negative, it gives up the negative spots for larger numbers, that will always bring in a 0. So it's really going to divide by a power of 2 there, always. I guess left shift does too, but that's how you think about it. So that's that. Let me show you left shift then on 5. Again, in older CPUs, it was faster. When you said divide by 2 integer division, it was easier to do the bitwise shifting circuitry inside the CPU. It was faster. And so the compiler would generate this code if you said divide by 2. That used to be the case. Still, these days on certain CPUs, I'm sure it would do that. So that produces my 2. 5 divided by 2, integer division. 5 right shifted by 1 gives me 2. All right, does that make enough sense? So that's cool, I guess, multiplication and division, but I haven't shown you the coolest thing. Shifts are good for when I care about a certain bit. This is what we really like shifts for, because you don't even have to think, all right? Here's the idea, right? If I wanted to set the third bit of a number, right, I needed to OR. It's like if I had this number, and I wanted to make sure I wanted to generate that number with bit 3 set as well, I would OR with this number, right? 1, 0, 0, 0, that would produce a 1 here, and everything else would be the same. How do I get this number? Sure, it's the number 8, but there's a much easier way. This is the number 1, right? Because that's 1 looks like that. And it is, it's been left shifted by 3. See how easy it is to compute that exact number that I want to OR with? You kind of read it off. It's like, all right, I want to set the third bit. I will OR by 1 left shifted by 3. That creates the number with bit 3 set only. Isn't that beautiful? That is what this is good for. If I want to get the third bit of a number, then I'm going to AND by that thing. I'm going to take this number, I don't know, 0, 0, 0, 1, and I'm going to AND with this thing. I want this third bit. Cool, give it to me. I'm sorry, 1, 0, 0, 0. And this will produce all zeros because it's not set. But what is this number? But again, 1 left shifted by 3. Isn't that lovely? Because you start with 1 and you left shifted by 3. That brings in 3 zeros. That's exactly the number that we care about. And this works for any number that you wanted to like set things like regardless of the number. Like if it was this one. If it was 1, 1 instead. it would still work. This always works for any number. Like it would take that number and put a 1 there. It would take this number and extract it just this bit. Still a 0 in the output. It's preserving all this stuff and making sure that there's a 1 here. I will OR with this guy, I will AND with this guy, and that is the power of bitwise operations. If you really want a bit, you're going to use a shift, and then you're going to do whatever operation. Okay? So that's the goal, and let me show that to you. So here was, let's do what we did already. Like I tried to extract the third bit of this number, and I ANDed with 8, and that was a little silly. Let's fix that now. Here's the better way. 11 ANDed with a number with the third bit set, whatever it is. I don't care that it's 8. Okay? And then same with this one. I wanted to set the 0th bit of this number, of number 10. So again, I will OR that with a number with the 0th bit set. It's just, I don't even have to think. It's 1 left shifted by 0, but I guess you could have just put a 1 here. But still, it works for anything. If like the user told you what bit you wanted to set, you just do that. Perfect. So that would give you exactly what we had before. And that is the much cleaner way, less thought, and we get our answers. Any questions about that? That's the power. That's where we're going. Alright, if we're happy, here is here's my thought. Here's a question for you again. I'd like you to write some code that toggles the 4th bit of an int named x. So again, somebody gave me an int x, maybe the user did. I have no clue what it is. It should work for any of them. What will you say? Again, you can do it in 1 line if you really wanted to. You can do it in more lines than that if you get stuck. But I know that you have the tools to at least do it in multiple lines right now. There is a trick to do it in 1 line, though. I would like you to toggle the 4th bit of a number. So, like, if this was our number, here is 0, 1, 2, 3, bit 4, bit 5. Your operation should take this number and produce 1, 1, right? Change the 0 to a 1, and then everything else is the same. And if this were the number now, your code should do exactly the same thing and make sure it's a 0 now. So you're not sure if it was a 1 or a 0, depending. Doesn't matter. Your exact same code should take this number and bring it back to 1, 0, 1, 0, 1, 0. Does that make sense? The same code should be able to both set and unset this bit, regardless of what it was. Alright? So that's the goal. See if you can figure it out. I know you can do it with a bunch of ifs and like and to extract or to set if it was a 0. There is a trick though. See if you can figure out the trick. It becomes a 1-liner if you do something. Okay, that was my timer. Alright. I know you can do it this way. I know you can be like, alright, check if this bit was set. You would AND with the number with just the 4th bit set, right? Put that in an if statement. Make it be an if else. If it was set, then you gotta, or sorry, if it wasn't set, if it was a 0, then OR it with a 1 in that position to set it. Else, AND it with a 1 everywhere but there to unset it. Yeah? So we did that on the previous example. Did anybody find the trick, though? What bitwise operation could we do to do it in one fell swoop? Let me show you. So say this was the number. This was the first one, 101. What is an operation that will toggle? Make it a 1 if it's a 0, 0 if it's a 1. The secret is to think back to exclusive OR. Watch. If I take this number and I exclusive OR it with a 0 everywhere with the bit I want to toggle, and then I put a 1 there, watch what happens. The exclusive OR with 0 it will make it a 1 if they're different. So that means it'll make it a 1 if there was originally a 1, which is perfect, and a 0 otherwise, 0 if they're the same. It'll preserve everything that just fine, just like an OR did. But this one, if they're different, it will set it. So exclusive OR becomes a 1 here. Do you see how it just made a 1 in that position? And I could take the same number. I could take the same number, or this new number, and exclusive OR it with the same thing. Exclusive OR it with a 1 right there in the bit that I want to toggle. Watch what happens. It preserves everything else. And then this guy, they're the same, so it makes exclusive OR becomes false. So that makes a 0 there. Beautiful. So that's the trick. Therefore, moral of the story is exclusive OR with the special number with the 4th bit set, which is 1 left shifted by 4. So take X, exclusive OR it with 1 left shifted by 4, and there's your answer. Any questions about that? So you can totally do it the long way with an if else and check for bits and things, but you can do it quicker with an exclusive OR. So that's fun to think about. But either way is the correct answer. Either way would get you points on a test. Alright, any questions about any of that before I just say one last thing? You probably don't care too much about binary. Like, you never think you'll use it. Like, you're just going to do decimal stuff all day long anyway. What's the point of having this lecture? So let me try and explain to you a couple good reasons why you might want to care about this lecture and remember bitwise operations. The first main one, near and dear to my heart because I studied programming languages as a grad student, if you make a compiler, your job is to make machine code. This disgusting stuff, when you accidentally look at the file the wrong way, right? We've all done this, right? This is your machine code. This is the 1s and 0s that make up the program that's running on the CPU. You must produce that as a compiler. And so the way that you do that is you flip some bits. There's some special bit patterns that correspond to instructions on a computer. So dump -d bitwise, just quickly, let me show this to you. Here's the main function. Let's find it. There it is. These disgusting things. This is the hexadecimal encoding of the instructions running on the CPU. These are the 1s and 0s, encoded as hexadecimal. And I think you can tell, like, some of these move instructions, that start with MOV, 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 they all start with the 48 byte. Those 1s and 0s, but whatever you're moving changes. Like, that's 48, that one, 48, 895, 48, 89, C7. So you have to change individual bits to make sure, like, oh, it's that kind of move that I wanted when I'm emitting that instruction so that the CPU can run it. So that's one thing that this is good for. You're making a compiler, if that makes sense. You gotta remember all the bit patterns and set them in the right way, because that's what the CPU wants. It wants that exact instruction encoded with that exact binary number. And then also, just like if you're working with any kind of file that's not text, like if you're going to read an image, like you work for Adobe and you're working on Photoshop or something, if you want to deal with image files, you have to extract the individual bits of however that image is encoded. It's like it's packed in a weird way. Like a couple bytes tell you how wide the image file is, a couple bytes tell you how tall the image is, and then it starts giving you like a big long array of bytes for every color inside of that image, for every pixel in order. And so you have to go and you have to extract all of those, each piece, one by one. And so you'd have to deal with binary files, and like I'll read a bunch of stuff and I want to get this byte out of it. That's the red part of this pixel. This is the green part of this pixel, etc. So that's another reason to care. Hopefully that made at least a little bit of sense. Any questions about any of that? Because I think that's where I want to stop. So fun ideas. We don't know enough to like do this yet, of course, but just have it in the back of your mind, I think. That's the reason. We had some toy examples today, but it goes much further than that, I promise. So yeah, that's all I wanted to do today. The rest of the time is yours to work on stuff that's already out.